Section 2.1, limits and continuity. All right, we started this yesterday, so can you guys remind me of a few things as we try to recap and then go into the rest of 2.1, starting into 2.2, hopefully. When we are looking at the informal definition question, what word, if I was to pick one, what word is most crucial for you to remember that defines what a limit does or is? Nick. Loud and clear. Approaches. It's listed twice. The arrows in limit notation are shown twice in the sense of what it means. So when we say down here, the limit as x approaches a of f of x equals L, I am coming from the right, I am coming from the left, but where am I looking for the answers to my limits? At the y values. I'm looking up to the heights, I'm looking up to the function. I'm looking up to the function values, I'm looking up to the y's. Okay, moving on. That was the most important thing for you to hold on to, for you to grasp from. The informal definition of a limit. Of course, we looked at representations of different fun things at the bottom and then the top. At 1/6 is really a limit. What? Okay. Then we started solving limits. What was the first way?
Numerical.
Which uses a calculator usually, and a table. Yes, I agree. So when we're using a table, remember, if they do not specifically state for us what side to come from, what do we need to check? Both sides. And limits only exist when one-sided limits from either side of a constant agree, otherwise known as, if the limits from either side do not agree, then the limit does not exist. Good. So then moving on, we practiced a little bit more with another function. You guys practiced with the table, you checked it, and you were able to find coming from the left it's 3, coming from the right it's 3, and then that means the overall limit, since they agree, is 3 as well. All right. We didn't get as far as grade 1. That's good. In the sense of, it'll be on the video. Okay, graphically. Sometimes, graphically, you're using your own graphing calculator, but more often than not, you are using a graph that has been given to you, and usually without an actual function attached. Usually just the graph itself. So with limits, they love to give you functions with discontinuities or piecewise functions. It really makes you stretch. It really stretches you in the sense of your understanding of limits. So, because of the definition of the limit, graphically, very similarly to numerically, also involves approaching from the right and the left, because I have to approach from either side, and it will only exist if it agrees, of the constant that x is approaching. Once again, just like numerically, with any limit, what am I looking at for the answers to my limits? The y-axis, kind of. Y values. That's probably the best way to fill it in. The y values. And I've been saying, look to the heights. Look to the heights. You're coming from the right and the left. Yes, you're coming from the right and the left. Yes. But look up to the heights. Look to the function. See what it's doing. That's even biblical.
Wow, I get it.
Where does my help come from? It comes from the Lord. Look up to the hills. Okay. I'm approaching. Look up to the heights. Look up to the function. Because these, the x values, are not my answer, right? The heights that I'm approaching, as long as they agree, that is my answer. So therefore, how would you guys write the problem and the answer for the graph that is shown if you're approaching the hole? What would be the problem? If you're approaching the hole. Good, has to be of a function, so we're just going to label him f of x, because who knows, not me. Maybe I do, it might be a square root translated. But equals what? Do you guys agree? Yeah. Now, is the only limit you would ever take of a graph that looks like this at the hole? No. Wait, what did I say that was weird that technically is kind of incorrect? I said at the hole. Do I take a limit at a hole? No, I take a limit as x approaches the hole. Okay, let's say it better. So, could you only find the limit as x approaches this hole? It's getting worse and worse. Maybe I should just erase that. Okay. Can I find another limit? What would the limit be as x approaches 3? Ish? 2.5-ish, right? So just because there is a hole, does that mean that I have to worry about like approaching anything else? No, it just means, okay, the hole itself wasn't even a problem, right? So I'm not going at, by definition of a limit, I am approaching. But I could also find it somewhere else. It doesn't have to be just at the hole, but obviously that's what I was trying to illustrate in this problem, right? Keep going with graphically. Even though you've already seen this with tables, I would rather show it to you with graphs because that is a much better visual for when limits do not exist. And I'll tell you now, the most important one for you to grasp, for you to catch hold of, for you to understand is part A. Limits will not exist, limits do not exist when you approach from the right and from the left, and each of those one-sided limits are not the same. When they disagree, which is what I've been saying, right? When they disagree. So a quick example of that. Now, I'm not saying that there are no limits that exist in this function itself, but what I'm saying is the limit as I approach this discontinuity, as I approach, wait a minute, what kind of function is this? Can you tell already? Oh, yeah, it's a piecewise. And not just a piecewise, what is the constant that's being put into those weird restricted domains? C. X is going to be greater than or equal to C and less than C, right? So C, those separators in the piecewise, those can cause huge problems, but I'm just talking about not every value, not every x value, specifically at C, that separator. In this instance, the limit as x approaches C of f of x does not exist. No possible answer whatsoever. I can't even state it. I can come from the right and give an answer. I can come from the left and give an answer, but do they agree? No. Now, B is a tricky one, and B is a very, 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 very technical. It's a technicality. Let's put it that way. It's a technicality. Are there two L's? Doesn't look right.
No.
English.
Math.
That was not helpful. I was talking about the English language and how we have so many different rules for so many different words. Okay, come back. Really? I don't know. Anyway. It's very technical, what I'm about to tell you. And we're actually only going to use it a couple times, and then I'm going to say, but actually, you know what? There's a better way. So even though it does not exist, let's put this as the answer. Yeah. So A is like does not exist, does not exist, does not exist. There's no way it exists whatsoever. B is a technicality because it's not approaching a constant. But it might be approaching and agreeing on an idea. Not approaching a constant. Is it approaching in your definition? Hold on, let's go back for a second. Is it approaching? In part B, look at it. As I come from either side of C, is it approaching a single number L from the definition? No. But some of you already know what I'm going to tell you in a couple slides. There is an answer that we write because it agrees. We can express what it's approaching. It's just not a single constant. So technically, it does not exist, but we're going to wait because there's still an answer. So it does not exist technically, but we are going to still express it as an answer. So in this one I will say, let me zoom in just a little bit. The limit as x approaches C of my function, which if you guys can tell looks kind of like a what basic function?
Oh,
Translate it just a little bit to the
left or no, right. One of the
right.
Yeah.
The L makes left, right? That side. Okay, that one. Okay, so it looks like a 1 over x squared has been translated to the right, but for right now, the limit of that thing, whatever that thing is, which you guys are pretty right, equals, and I'm just going to put a question mark. It's not a constant, so it technically does not exist, but we're definitely going to answer that, and we're going to definitely express it with an idea once we get there to talking about infinite limits. Okay, last one, part C. And actually, I'm going to go ahead and move this C just to make it match an example that I'm about to show you and have you guys look at. Actually, some of you asked if we needed our graphing calculators. You don't need it, but you can use it in just a second to see a weird, funny function that looks something like... if I'm oscillating between fixed values, and if as you zoom in and zoom in and zoom in and zoom in and try tracing and try with your tables and numerically and all this jazz and that, okay, it might be a little different with the curly cues, but that's the main idea going on in the middle. Yeah, the limit as x approaches C when C is at whatever point that oscillation craziness is going on. That definitely does not exist. Let me go ahead and give you an example. In your graphing calculators, go ahead and graph really quickly y equals sine of 1 over x. You might not believe me, or you might not know what it looks like when you find it. So go check out y equals sine of 1 over x. Find me the limit as x approaches 0. Find me the limit as x approaches 0. Do what you can. Oh, those of you guys that aren't looking, you probably go first.
I told you to zoom in. I did. It just was worse. Yeah, look at that. He broke my calculator. You can freak someone out.
Anita's done. Who else got it? No, I think barcodes have a finite number of lines. Infinite enough.
It's not awesome.
Oh, Chelsea's done today. Nice.
For math?
No, I don't know who Chelsea is.
You don't know who she is? Like, you know who she is or you don't know her?
I know a Chelsea, but I'm not sure who that is. It's not?
Oh, yeah.
Oh, yeah, what about you? None of them even, they all hate me.
They're gonna ask me to do
Just you. I remember her.
Can we though? Alright, what happens when you zoom in and you zoom in and you zoom in and you zoom in?
Your calculator breaks.
No, it shouldn't break.
Not yet.
It shouldn't break, but it just sounds a little bit funny.
Whoa.
Hold on. My zoom's off. You guys know how to break the calculator from thinking, right? Like, stop them, break them in its code.
Take out the battery.
Hit on or hit enter. Enter kind of pauses them. On actually breaks it. Okay, so it looks like the limit is 0. But to make sure, what should you do? Put in the
Zoom
Put it in the table.
Zoom in. Maybe put it in a table or zoom in. Okay, it doesn't look too weird. I bet the limit's still 0. So let's zoom in some more. We're going to zoom in some more.
It's Batman?
Okay, if we just zoom in enough, it's going to be okay. Did anybody keep on zooming in?
Yeah.
Try.
Does it get better?
Barcode.
It looks like a barcode. Whoa.
Wait, okay, but wait, it's approaching. Look, I can see it. Okay, so let's go ahead and try. So if we plug in 0, does it exist? No. Okay. So what if we plug in like 0.1? Now what is it? Okay, negative a half, right? Okay, let's get a little bit closer. So what if we plug in 0.003? I'm just getting closer but not using the 1. Now it's wait, is that a positive?
Yeah.
Oh, crud, that's a positive 0.3. Okay, hold on. It's still getting closer to 0. I bet it is. So let's go ahead and do, not a negative. Let me try from the other side. Negative 0.00007. What's going on? It's oscillating as you zoom in, zoom in, zoom in, zoom in. What's going on with your calculator is he's like, I'm freaking out, so he kind of leaves part of it blank in the middle, but it's, yeah, he's having issues. Is there a limit? No, it does not exist. Does not exist. Real quick, guys, at the bottom, if you didn't already write the note. Note, a limit only exists if the answer is a real number. Technically, the limit only exists if the answer is a real number, which is what's going on in B and what's going on in C. C is does not exist, does not exist, does not exist. A is does not exist, does not exist, does not exist. B is does not exist, but we're going to try and write them as an answer in a little bit. Special limits. Is this about B?
It's about A.
Oh.
A wasn't a real number.
From one side it was, and from the other side it was, but it sure wasn't the same one.
But
it wasn't the same one. Go back to the definition of the limit. The limit says as you approach from either side.
Oh, I'm sorry.
Okay, no, it's okay. Special limits. One-sided ones, which we've already been talking about because you saw it last year, hopefully. One-sided limits. One-sided limits lets us take a problem like Nick was just talking about with part A, lets us break it down into its individual pieces and come from one side first and then the other side, which is technically what we kind of do in a graph and a table anyway. The only method of solving limits where we don't use the right and left is algebraically. But algebraically is totally like doing shortcuts, so that's why. Can you open the door for she comes in? Thanks, Maggie. So if it's positive, guys, if my sign in my exponent just as a symbol, the limit as x approaches c positive, where am I coming from? Think from positive infinity, so from numbers on the right of wherever I am. Right, and if I'm doing the limit as x approaches c negative, these notes will be online. How'd you be missed? I'm coming from numbers on the negative infinity side, so therefore from the left. So if I were to give you a problem, an example, a graph like the following, I want you guys to find me the limit as x approaches c from the left, the limit as x approaches c from the right, and finally, the limit as x approaches c of f of x. And my function is like a 7 by 7-ish %. Let's see over here. Limit from the left, limit from the right, and the limit all together. Limit from the left, limit from the right, and limit all together. Alright, Kayla, as I come from the left, where are the heights? Where are the heights approaching? From the left, where is it approaching? 7. From the right, where is it approaching? From the left, he's approaching what? 7. From the right, he's approaching what? 0. And the overall limit is? Why? Because the one-sided limits do not. Because the one-sided limits do not. Because the one-sided limits do not.
Exist.
No, that's not it. The limit does not exist because the one-sided limits do not agree. They do not approach the same number. So they do not agree. And if they do not agree, then the limit cannot exist. Woo! All right, let's try again. Oh, that didn't work. So with the following graph, let's try a few more. Let's do the limit as x approaches -6. X approaches -4. As x approaches 2. And let's just start getting exciting. As x approaches. Fill those puppies in. Now, guys, can you see the graph off of the graph?
What?
You know exactly what the graph, is just looking at the portion of the graph that you're given. Are you able to make any other assumptions beyond what they've shown about what's going on outside of this little window of the graph? No, so you're going to have to use what you see. Okay, we're just going to assume that whatever you see continues, just in case you're wondering about part D. My football guys, chapter 1 homework packet, AP number 1, all those grades haven't been put in yet. And the quest hasn't been put in yet. So I wrote a quick note just saying that grades will drastically change once a couple more things get in. All right, as x approaches -6, guys, what's my limit? I didn't do one-sided, right? So just think about both sides. How come? Look to the heights. And where is he approaching?
4.
Got it. How about part B? Does not exist because as you come from the left, what's the limit? As you come from the left, what's the limit? 1, 2, 3, 4, 5, 6. Good. As I come from the right, what's the limit? Ooh, those don't agree, so it does not exist. How about the limit as I approach 2? Yes. What is he approaching? 2. Do I care about what's there? I do care about it because it makes it discontinuous. There's a hole, but I don't care about it for a limit because the limit just says what is it approaching. So it's 2. And then last but not least, okay, what is my limit as I go to infinity to the right? So therefore, look to the height, look to the function. Where's he going? Wait a minute. He's not going to a constant though. But can I express him as what he's doing? Where's he going? And if I don't write a sign, what do I assume that infinity has? A positive sign. Good. Questions, judges?
For when it's approaching 2, there's a dot.
Yeah,
There is a dot.
Yeah.
That's what's at x equals 2. It's a piecewise function, so you have a normal function with a whole, like a denominator factor, which has 2 as its 0, and then it's on the top and on the bottom, and then they have like this extra point that's defined in a silly piecewise function. It's at 1, but where is it approaching? 2. Does that make sense? Josh, go ahead. All right, infinite limits. So we were just talking about, if it's going to infinity, why don't I just write infinity? All right, let's keep that up then. So, if I have graphs, where as I approach, as I get closer and closer and closer to, as x approaches c, if I have graphs that are increasing and or decreasing without bound, how do I handle those? Well, let's check them out. He should be a little closer, I think. Should be a pretty easy idea, but just to make sure we're all on the same page. Assuming that the functions are what's shown in the graph. Alright, kiddos. What am I going to say is the limit? If I want to express what it's approaching, whether or not it's an actual constant, what would I say for part A?
Infinity.
Infinity, right? How about part B? Why, Cassidy? Why doesn't it exist? As I come from the right and the left, the limits do not agree. Thanks, Nick Davis. They do not agree, so therefore the limit does not exist. Last one.
Is that R?
R? What is R?
The R under limit.
That's a C.
Oh, okay.
Where's he going?
Negative infinity.
Negative infinity. Negative infinity. Negative infinity. All right, guys, don't write anything down for this example. I don't think we need it. We could find a limit of this point, or that point, or that point, or that point. What's the limit as x approaches 4?
Infinity.
Positive infinity. Positive infinity. Ooh, what's the limit as x approaches infinity?
-1.
What? Is there a horizontal asymptote too?
I'll be -1. What if it just has...
We're not talking about limits to infinity yet, technically, even though we talked about it somewhat last year with end behavior, but right now, we're still talking about what happens if the function increases or decreases without bound as it gets closer and closer and closer to an x value from either side. If I'm going to change it a little bit. If the one-sided limits as x approaches a are, now my grammar's off. If the one-sided limits as x approaches a are either positive infinity or negative infinity, then there exists a, what was there in all of these examples? All of these examples at the constant I was approaching. If the function increases or decreases without bound as I approach a set x value, what's going on? What exists at C? What kind? Vertical one. Oh my goodness, you guys are dead just because my air turned off.
Yeah. It's the air.
The limit, the one-sided limit as x approaches a are either negative or positive infinity. There exists a vertical asymptote at x equals a, and technically that's the definition of a vertical asymptote. All right, kiddos, I want to reward. We are going to section 2 too. How did this take so much longer? We weren't as ahead as period 1. Bummer. I want to reward. We won't go to section 2.2. But if you think about it, section 2.1, we talked about the definition of a limit. The key word is what?
Approaches.
Approaches. And limit answers are what kind of values?
Why?
Why? Look to the height. Look up. Or look at the negative height. Look down. Okay. Hold on. What 2 ways did we see or did we practice in review of how to find limits?
Numerically and graphically.
Numerically and graphically. Good. So what do you think section 2.2 is going to be all about? Algebraically, which is the way most of you guys will like plugging in. And if it doesn't work, 0 over 0, keep going. And we'll see it. Okay, hold on, class. I want to reward, since we have a couple minutes left. Don't you know? I want to reward those who did start their homework last night as they were supposed to. Are there any questions yet on homework 2.1? Laura, 16. Anybody else?
22.
22. Anybody else? How do you guys all at the end? This morning they were all in like 3 and 6.
Can we try number 10?
You
Or
just.
the elite and training.
Ooh, number 10 is good too.
Okay,
Okay, I'm going to help first of all with number 16 and 22, just real quick. If they are giving you decimals, hold on, think. If they are giving you decimals and saying something like find a limit or approximate a limit, what are they asking you to do?
Find the limit or
We only did limits 2 ways this section, so if there are, Sterling and Sunny, shush. We only did limits 2 ways this section, so if they are saying find a limit and they give you certain decimals for x, what are they telling you to do? Plug it in. Use a table. So in number 16 and number 22, both of them basically, to some extent, you're setting up a table for whatever the function is that they have given you, and you are plugging in different values. Like for number 16, they're telling you how to approach 1, negative 1. They're telling you how to approach negative 1. They're saying, hey, plug in 0, plug in 0.5, plug in 0.9, plug in, these are all negative, plug in negative 0.99999. They're telling you whatever the numbers are, how to approach. Does that make sense, Laura? They're telling you how to approach. Whenever it says CAS, it's talking about a computer graphing calculator, basically like this huge old graphing utility. We don't have it, so don't worry about it whenever you see CAS. Number 22 is kind of similar, but it actually points out a flaw, so it's going to be kind of weird. Just hang in there. Benji asked about number 10. Is that a homework problem? Number 10. Guys, for number 7 through 12, the point is to sketch a graph. If it says sketch a function, how many graphs am I doing? 1. But hold on. Number 10 gives me 4 different characteristics. It says this has to be true, and this has to be true, and this has to be true. But wait a minute, how am I supposed to do that if I'm only making... Oh, that graph has to have all of those characteristics. So hold on. In number 10, part 1, it says the domain is 0 to positive infinity. Okay, I know to only make it 0 to positive infinity. Part 2 says f of 1 equals 0. All right, cool. When x is 1, y is 0. Keep adding and see if you can figure out a picture, maybe not the only picture, but a picture that meets all of those conditions. Bye, guys. Happy weekend. I am not here after school, remember, but I'll be here during lunch if you have any questions. I'm not here after school, remember, but I'll be here during lunch if you have any questions.
Yeah, these.